Hello, this is Ahmed Al Hadrami. This presentation is for ME 496, Video Assignment 2. Our problem statement here states a source of strength M is located at distance L from a vertical solid wall. The velocity potential for this incompressible irrotational flow is given by our phi velocity potential expression. We will come back to it in a second. Let's continue reading the question. Our first part of the question wants us to show that there is no flow through the wall. Our second part of the question wants us to determine the velocity distribution along the wall. The third and last part of the question wants us to determine the pressure distribution along the wall. Assuming P equals P naught far from the source, neglect the effect of the fluid weight on pressure. Let's take a look at our velocity potential function. It is the mass flow rate over 4 pi multiplied by our scalar function. It is important to know that our mass flow rate is related to our volumetric flow rate. This is our volumetric flow rate, and the mass flow rate is a measure of the mass of our fluid in the system per unit time. Let's take a look at our diagram. We can see that we have a source located at a distance L. We have a wall, which is our surface boundary layer. We know that sources, the flow field of sources act in a direction outwards of the center, whereas for a sink, the flow field direction will be pointing inwards. We also know that the flow of the fluid is submerging from the single point right here, which is where the fluid is supplied at a constant rate. This point is known as the central common point, where all the streamlines meet. We also know that the velocity decreases as area increases. So as the area increases, the velocity decreases. So the relationship between the velocity and area is inversely proportional. We can see that by how the streamlines spread out. I forgot to mention a very important principle about how forces develop. As we discussed earlier in our first presentation, forces will develop due to fluids being in contact with a surface. This is our surface, the wall, and our fluid submerging from the single point towards all directions. We are trying to find the velocity distributions and pressure distributions along the wall and to prove that there is no flow through the wall. And to approach the problem the most fit method, we will have to note down our givens in the problem. We know that we are dealing with an incompressible and irrotational flow, and this leads us to the Navier-Stokes equations. Navier-Stokes equations gives us the velocity in the x direction, the velocity with respect to the y-axis, so the y component of the velocity, and the z component of velocity. So we have reached or arrived at this principle or those equations from the Navier-Stokes equations that have been derived in class by noting down that our velocity potential is incompressible and irrotational. It is also important to remember that we are neglecting the effect of the fluid weight on pressure. We can hold on to this thought and we will come back to it when we need it for part C. Let's continue tackling our problem. Let's start with part A. To show that there is no flow through the wall, we want to show or determine the value of the velocity at this point. Also, we do know that the velocity can be expressed as the gradient of our scalar function. So the gradient of our scalar function is our velocity. We can show that there is no flow through the wall using two different methods. We will focus on the first method that utilizes the Navier-Stokes equations. Before starting part A, we need to establish our axes. We do know that we are dealing with a 2D plane. Our problem is a 2D problem. And we are given the terms, we are given the potential velocity in terms of x and y and L. And as we said, because we are dealing with a 2D flow, we are going to eliminate the z-axis. For part A, let's find the velocity to prove that there is no flow through the wall. We do know that the derivative of our function is nothing but the tangent line of our curve or our function. So taking the derivative with respect to the x-axis, we are differentiating the potential velocity function m dot over 4 pi. Now we take the derivative with respect to x. The derivative for this function is not as complicated as it looks. We only have to remember that the derivative of the natural log is 1 over x. So ln of x is equal to 1 over x. So the natural log of this whole expression would be 1 over the entire term, and then we differentiate the term because of the chain rule. So I will start here right away by taking the derivative. As we know, this is the term phi. Our derivative will be 1 over the entire term multiply, and now we differentiate what is inside the term, the chain rule. So 2 multiplied by the base, the bracket as it is, minus 1 from the power, plus 0 because we are differentiating with respect to our x-axis. So our y squared is a constant. And our second term will follow the same way of differentiating. We have ln of x plus l squared plus y squared, and we differentiate the term, the power multiplied by the base, minus 1 from the power, differentiate what's inside the bracket, which is just 1, and the derivative of y squared is 0 because it is a constant, as we are differentiating with respect to our x-axis. And if we are interested about the velocity about this point, the moment where there is an impact between the fluid and the boundary surface layer, then we plug x equals 0 in the equation. If we plug zeros here, we are left with a 0. And I hope this explains why there is no flow through the wall. We do know that the flow path, the path of our streamline, is along the x-axis. It keeps traveling until it hits this point. So our streamline is a path of our moving particle, and we are trying to prove that this moving particle will not go through the wall. U equaling 0 means this moving particle is being stopped by the wall, as it cannot pass through it. So no flow through the wall. And the second way I was thinking about proving this is by reviewing some of our calculus. We do know that our velocity can be expressed as our gradient of our velocity function. So if we take the derivative of our function, we determine the tangent line, and the tangent line is equal, the gradient is equal to the slope. So to show this, let's imagine we have let's draw the source one more time. Quick rough sketch. So we do know that the velocity is always tangential to our streamlines. So we do have a tangent along those streamlines. And for our flow path in this direction that I forgot to put, our tangent is parallel to the x-axis. And if our tangent is parallel to the x-axis, in this case, that means we don't have a rise, but we do have a run. So we can determine a slope of 0 since it follows the form of the gradient. In other words, the velocity is always tangential to the streamline, and we can see that there is no velocity in the x component because our gradient is 0. Just a quick review. d dt of our function is equal to the gradient is equal to the tangent line, and then we can calculate the gradient. And let's move to part B. For part B, the question wants us to find the velocity distribution along the wall. Before starting, I forgot to mention about one more thing about part A. Since our tangent is on top of our flow field, or on top of our flow path, which makes it parallel to the x-axis, it means it's a constant. And if we take a derivative of a constant, it is 0. Whereas in the other curves, we do have a slope because we have a rise and we have a run. So we will have a value for the velocity in the y direction. By using the Navier-Stokes equations, we know the velocity in the y direction and I will take the derivative of our potential velocity with respect to the y-axis. We will pull out m dot over 4 pi constant and take the derivative with respect to the y-axis. I will take the derivative right away. We have our function written here, so I will differentiate it right away. Our derivative with respect to the y-axis will be, okay, as discussed, the differential the derivative of the natural log is 1 over x. So we can do 1 over the entire term, x minus L. But now we are differentiating with respect to the y-axis, so 2y, and our first term goes to 0 because it is considered as a constant. And for the second part, the natural log of the whole term, and the derivative with respect to y. This gives us x and we are trying to find the velocity distribution along the wall. I can keep going, but I would rather substitute for x equals 0 because we want to find the velocity distribution along the wall. So substituting x equals 0 takes away my x term, and we are left with, okay, I'll write it out, sorry. Over L squared plus y squared plus 2y over L squared plus y squared. Same denominator. And we did have the mass flow rate constant here. Our force cancels out, and we are left with m dot over pi and this is our velocity distribution along the wall. If we would draw the pressure distribution of our velocity, distribution along the wall, it would look something like this. So we did say at x equals 0, this is our wall. At y equals 0, velocity equals 0. And for y greater than 0, y less than 0. The velocity distribution is acting in a way, in a parabolic behavior. So this curve 1 and curve 2. So this means that our velocity distribution is increasing from the wall surface to the source. As we said earlier, that we do know velocity decreases as area increases, so our velocity at this point, the central point, is at its highest here. The velocity at this point is the fastest at this point. And as we move away from the central point, the velocity decreases. The velocity decreases until it hits the surface boundary layer. So if we would look at the behavior of the velocity relative to the wall, the velocity is increasing as we move from the zero axis to our central point of our source. So our velocity increases until we get to the central point. And as we go in this direction, our velocity is decreasing because now we are getting away from our source. So let's imagine this is our source center point. This is our center point, and we said here the velocity increases as decreases, the velocity decreases as we leave the single point, which is the point where the fluid is supplied at a constant rate. So in relation to this, we are trying to relate those two pictures. I said the velocity is increasing as we leave this point. So the velocity is decreasing from the single point to the right side, from the single point to the left side. Whereas in the velocity distribution, we can see it clearly that at the center, we have the highest points of velocity. And then as we get further and further away from our central point, our velocity is decreasing and decreasing. And the same analogy for part B, we are taking the derivative of a function, and the derivative of a function gives us the tangent line, and we can find the velocity gradient from the tangent line. Here our velocity gradient was 0 in the x direction, and for the y direction it was not 0 because we had a slope, or we had the gradients. And for part C, I hope that view was clear. So now I am going to approach part C, and for part C we have to use the Bernoulli equation. And do we remember when at the very beginning at the problem I asked to hold on to a thought about neglecting the effect of fluid on pressure. So we do know, like, neglecting the effect of the fluid weight and pressure, if we neglect that, the fluid is acting at the center of the mass and pressure is acting opposite to it, there will be no shearing stress. And that means our fluid is not viscous or inviscid fluid. We can prove that from our very first few weeks in this course. Our shearing stress is equal to the viscosity multiplied by velocity over distance. So if the shear stress is 0, then our viscosity is going to be 0. That means that our fluid is inviscid. Our fluid is inviscid. It is important to note down that our fluid is inviscid because using the Bernoulli equation for the irrotationality, the conditions or requirements are three, which is inviscid fluid, steady flow, incompressible fluid, and irrotational flow. We are pretty familiar with our Bernoulli equation. One half density velocity squared plus density z2. Just separate these two parts. This is our part C. We do know that both of our streamlines are along the same streamline, so there is no height difference. Therefore, we can cancel out our z1 and z2 terms. And the problem statement says, assuming P equals P naught far from the surface. So P1 equals P naught one half V1 squared equals P2 plus 1/2 V2 squared. We did determine that our velocity is 0, so this term goes away, and we are trying to solve for the pressure distribution along the entire wall. So if we would draw our streamline between the 2 points, it is between the point in the sink and the point at the wall. We do know that the pressure at the wall is going to be we solve for the pressure at the wall. Let's name this velocity of the wall. This is P2 is pressure distribution at the wall. So solving for P2, we get squared, and our velocity at our second point was calculated as V at the wall is this term, the whole thing squared, and I forgot to add the m, mass flow rate over pi. So this simplifies down to the whole term squared, and this is our pressure distribution along the entire wall. I hope that you were able to view the last part as I was discussing it. I have a feeling it was not recording the last section. Anyhow, I will go over it again. For the last part of the question, we approached it using the Bernoulli equation. We were given that P equals P naught, and we are solving for the pressure distribution at the wall. We do know that the 2 points align on the same line, so Z1 and Z2 are the same height. We do know that we have calculated the velocities at the different points in our problem. So what we did is we have simplified our Bernoulli equation as much as we can using reasonable analysis or reasonable assumptions to simplify our equation as most as possible. And I hope I covered everything in the problem. So to understand the problem, one needs to know the Navier-Stokes equations and of course understand calculus 1 and 3, and being familiar with the Bernoulli equation. And to prove by mathematical representations, we draw the tangents and use it to explain our understanding why such components are zero and others are not zero. We did say that we do know about that sources flow in a direction outside the single point being the point that supplies the fluid at a constant rate. And yes, I hope I covered everything. Thank you very much. This is Ahmed Al Hadrami. Thank you.